Welcome to our next lecture in the series on condensed matter theory. In this video I want to talk about crystal field theory. And crystal field theory is actually one of the oldest methods to describe properties of solids. Shortly after the introduction of the Schrödinger equation, it was pursued by people like Bethe or van Vleck, very close to the founding fathers of quantum mechanics. And it has of course a lot to do with being able to describe atomic spectroscopy, but then for materials inside solids. It was very well realized in the beginning that, well, you have the atomic spectra, and when you put atoms in solids, then for some materials there was hardly anything left of your atomic excitations. But if you put a transition metal in a glass, for example, you have wide bandgap insulators with some open D and F shell elements in there. Then the spectra that you saw were atomic-like with severe modifications to the energies and intensities that you saw. Now, and crystal field theory is developed exactly to describe these kind of materials. What we have seen in the previous video is that we can describe our material starting from a single atom, and we're going to neglect all charge fluctuations in our first approximation. In this case, we can write down our wave function for the solid as a simple product wave function where we have the atomic eigenstates on each side with a given configuration. If we now look at your local eigenstates, we have to look at the local atomic Hamiltonian. And this includes both the Coulomb interaction 1 over 4 pi epsilon 0 Ri minus Rj, let's put a half in front, plus the sum over the spin orbit coupling constant sum over I Li dot Si. And we want to find a way to add the effect of the lattice. Now, this will be our crystal field Hamiltonian, and our crystal field Hamiltonian is going to be a sum over m and m prime and the spin, and it will be some energy coupling state m with state m prime. And your full Hamiltonian that we need to solve for a single atom is then the atomic Hamiltonian plus the crystal field Hamiltonian. So we're going to answer two questions within this video, and that is how to determine those prefactors, what is the local crystal field strength, and then once we know what our crystal field strengths are, we're going to diagonalize the full Hamiltonian. Now, both of them are highly non-trivial tasks. Diagonalizing your full Hamiltonian is still diagonalizing the Hamiltonian of an open D or F shell, and although very quickly methods were developed to be able to do this, if you put 5 electrons in a D shell, there are already over 250 ways to do this. 7 electrons in an F shell, there are more than 3,000 ways to do this, such that the matrices that you get in between are non-trivial, and it took, well, maybe 10-20 years after the introduction of the Schrödinger equation before those equations were solved. At the same time, determining what your parameters are, what the microscopic reason is that you have your crystal field, turned out also to be highly non-trivial. And we will first focus on an historic explanation that people as Bethe and van Vleck gave to the crystal field, But that argumentation turned out to be not correct and not the real reason why you have effective crystal fields. And I'll show you a little bit in this video where your crystal fields originate from. And in a later video I will show a clear example of nickel oxide where we can go completely through all interactions that we have in that material. So it is because of those reasons, the original idea where your crystal fields come from, as well as diagonalizing the Hamiltonian, that is hard, combined with the mean field approximation that people like Fermi or Sommerfeld made, where you just neglect the Coulomb interaction completely, that then have people focus on the free electron-like models, which were very effective for describing the semiconductor physics, combined with semiconductor physics being extremely useful in all the electronics, which then after some years made people focus much more on the free electron models. And now, of course, when we understand our free electron models very well, plus the fact that we now have computers for which diagonalizing a 1000 by 1000 matrix is really no work anymore, that we can come back and visit the correlated electron systems and see what their properties are. So we want to look at two things, the microscopic model as well as the eigenstates. And let's first have a look at the microscopic reason. For our crystal field given by the parameters m and prime sigma, the hopping amplitudes from hopping from orbital with m prime to orbital m. Now, the method is developed for ionic crystals because we neglect all charge fluctuations. So we can think of something like lithium fluoride, where we say that we have lithium 1 plus and fluor 1 minus. Or nickel oxide, where you have nickel 2 plus, oxygen 2 minus. In both cases, when I make fluor 1 minus, it becomes the neon configuration, and oxygen 2 minus also becomes a neon configuration. So we get filled shells of the oxygen or fluor, which we will call the ligand ions in there. And then we have the nickel with an open D shell, where we want to understand what the crystal field is doing. So we have 8 electrons in this case on the D shell of nickel, and we want to know how these atomic eigenstates are influenced by the effect of the crystal. If you think of such a crystal, then you can say I have a lithium ion or a nickel ion, and it would be 2 plus. And then these are rock salt crystal structures, such that if you just look at a plane, you have alternating nickel and fluor ions, nickel and oxygen or lithium and fluor ions. Or if we look at the center, we have a nickel 6-fold coordinated by oxygen ions. Such that from nickel perspective in the x, y and z direction, both positive and minus, you see a negative charge. But if you would move along a 1-1-1 or a 1-1 direction, you would find a positive nickel ion again. So as a function of angle, we have a negative, positive, negative, positive, negative, positive, negative, positive charge, alternating with angles of 45 degrees. So this will give you a potential due to the charge. Now it is this crystal field potential that can be responsible for this effective interaction. Well, it turns out that electric potentials like this are extremely small in solids. So this microscopic reason is not okay. It is highly historic, but it does include the correct symmetry of the crystal. So if you include your sums in lucky and correct ways, you now and then get correct answers. And even if you include sums in incorrect ways, you get at least qualitatively the right direction in which you have to go. So that of course was highly encouraging for people in the beginning when they developed these kind of materials. But you have to realize that solids are neutral. Even the highest ionic crystals have very little charges moving between the lithium and the fluor. One reason for me to still start from here is because it gives you a nice understanding on what the microscope of what the ways are you can write down your Hamiltonian, and then the symmetries that are involved tell you what the parameters are that we are left with. And then of course if you treat those parameters just as parameters you fit to experiment, you will get correct answers. And later we will discuss a little bit how you could actually calculate these kind of parameters. So if I have a potential, either because you have charges that have a certain distribution or because my effective model is describable by a potential, and we want to know the eigenstates within an atomic shell, then we can expand our potential on spherical harmonics. And for that we have a sum over the angular momentum that we have in our potential, and then a sum over the z projection of our angular momentum. And we have some prefactor that depends on the material at hand. Then we have a polynomial in k, because I make an expansion on spherical harmonics in the angular dependence, but not in the radial dependence. And the reason you only have r to the power k comes from the Coulomb interaction, where if you think of the local charges having a Coulomb interaction with charges that are further away, then you have the angular dependence, the radial dependence, r to the power k of the smaller coordinate divided by r to the power k plus 1 of the larger coordinate in your Coulomb expansion, such that when we have potential, only this potential in k remains. Now if you want to calculate the prefactor of k, then we can make a Taylor series expansion, so we have to take the derivatives of the potential evaluated at the point r is equal to 0. We have our 4 pi over 2k plus 1 due to the expansion on spherical harmonics. Then we have the prefactors of our Taylor series expansion, k plus m and k minus m faculty, and then a derivative where we have to realize that, well, it's not just a derivative with respect to r, but we also have the spherical harmonics in there. So we have a k minus m derivative in the z direction, and then a derivative to the power m in the x plus y direction. And that's the sine of m in the x plus I dy to the power m of your potential, evaluated at the point r is equal to 0. So with that we can expand a potential on spherical harmonics. Now we know that our wave functions, or our one particle orbitals, can be written as a radial wave function times a spherical harmonics. And with that we can basically calculate the radial integral for each k value, and we can define a new parameter am of k, which is then given as the old parameter times the integral over the radial wave functions and r to the power k. such that we're left with a single parameter. And this is of course nice because, well, we do not really know what our potential is, and we already argued that it's really hard to calculate that from just some charge distributions, because we cannot just assume ionic charges in our crystal. And then, well, if you don't know your radial wave function either, you just integrate over both of them and make them an effective parameter. Such that in the end, our crystal field Hamiltonian is given by a sum over m prime and sigma, and then the sum of k, the angular momenta of your effective potential. And we don't have to sum over m, because in our integrals over three spherical harmonics we have these nice conservation rules. We have our spherical harmonics at m prime and m, such that the interaction in between has to be m minus m prime at k. And this is multiplied with a dagger n l m sigma a n l m prime sigma, spin conserving. And this is numerically a really nice way of expressing your Hamiltonian. Yes, it only leaves interactions between spherical harmonics and parameters in front. This is a very useful Hamiltonian. Do not treat AMK as some ab initio parameters, but we can always fit them to the experiment to get an idea of the effective crystal field that we have. Now, when you do this, we can realize that our clear selection rules of these parameters A and K and for the selection rules, we know that we have the triangular equations, which tells you that L minus L prime, so let's assume that we do not only have a look at inside one L shell, but we can have two open shells, then L and L prime would be here. If not, it's just L is equal to L prime. Must be smaller or equal to K, must be smaller or equal to L plus L prime. And at the same time we know that we have parity conservation, so L plus L prime plus K has to be even. We know that our Hamiltonian has to be Hermitian, which means that our parameters A and K have to be equal to minus 1 to the power m, A minus 1m K complex conjugated. Now, of course, we can write down our crystal field Hamiltonian with the parameters A and K. What we saw before is that we also can look at the scattering from orbital m prime to m, and the hermeticity requires you that m prime m is equal to m prime complex conjugated. Then we have symmetry. In our system, many of our transition metal or rare earth complexes have very high symmetry. Very often you will find cubic point groups, such that you have many symmetry operations that commute with your Hamiltonian, rotations, planar mirror inversions. And when this is true, then for your potential, we know that the symmetry operator acting on the crystal field potential leaves the crystal field potential invariant. Now let's have an example on such a crystal field. And for this we're going to look at cubic point group. And for that we have to see how our potential expanded on spherical harmonics behaves under the possible rotations that we have in our point group. And it is here where the expansion on spherical harmonics is really helping you, because there we have very clear ways to determine the symmetries and therefore the allowed expansion coefficients. If we think of spherical harmonics, then this is a polynomial in cosine theta times 1 over 2 pi e to the I m phi, such that if you rotate around the z-axis, m tells you how often your phase is changing. So if we now think of a symmetry operation or rotation, then we can quantize in the direction where we rotate. So we rotate around the z-axis. Such that a rotation by capital phi of your spherical harmonics is equal to e to the I m capital phi times that same spherical harmonics. So we pick up a phase e to the I m phi for a spherical harmonics with angular momentum L and projection on the z-axis m. So if we now want to generate a character table for a complete L shell and then project this on the character tables of the irreducible representations, then we find that the character table for a complete L shell is given by the sum for a rotation of phi of m is minus L up to L e to the I m capital phi, the trace of the rotation matrix. So that of course then allows you to calculate the character for each of the possible rotations in your group. Then you get a vector. This vector you project onto the vectors of the irreducible representations, and you will find how your D shell will split in a particular point group. And for the case of D orbitals, we find that they split into an T to G and EG states in OH symmetry. And the T to G's have a multiplicity of 3 and the EG's a multiplicity of 5, such that in total we have a of 2, such that in total we have a multiplicity of 5. So based on that we can have a look what the possible and allowed potentials are. For that we shouldn't have a look at how the basis transforms, but how the different spherical harmonics that we use in the expansion of our potential transforms. The scattering between two d orbitals can have an angular momentum of 0, 2 and 4. It has to be even, and L can go, or K can go from 2L to 0, from 0 to 2L, which is from 0 to 4. So our potential in the cubic point group expanded on spherical harmonics has the coefficient for your spherical harmonics at L equals 0, 4 pi over 2k plus 1, and then we have our expansion coefficient. And that of course can just be a number which tells you how the center of gravity of your system is changing, because this is the spherical component. But if we think of the T to G's and give them the energy ET to G, and EG's and give them the energy of the EG's, then your center of gravity has to be 2/5 times the energies of the EG's plus 3/5 times the energies of the T to G's. Now, if you look on the character table for L is equal to 2, then you find that you have a T to G and an EG irreducible representation. We also know that the potential must transform like an A1G irreducible representation. Under rotation it must come back to plus itself and not with a minus sign, or in a non-one-dimensional representation of the group, such that the potential at L is 2 is absent, but we have an expansion for the potential at L is 4. And if you then go through the exact representation, then you find that it depends on the energy difference between the EG and the T to G orbitals. And we have two parameters for the two energies. The 0th order depends on the sum, so the 4th order then has to depend on the difference in some way. Now, not only the Lz is 0 component, but also the Lz is 4 or the Lz is minus 4 component is allowed. The 4 and minus 4 have to be equal because we have Hermeticity, 4 pi over 2k plus 1, k is 4, so that's 4 pi over 9. And again, these prefactors can be derived if you go through all symmetry operations, but it's not so important for the moment. Other than that these parameters depend on the energy difference between the T2Gs and the EGs. Now this form is highly convenient if you want to make effective operators, where you do not only look at potentials, but we can make also operators in terms of the angular momentum L. And we know that A0 transforms like a spherical harmonic of 0 and A4 as a spherical harmonic of angular momentum 4. So we can immediately understand that if you look at effective operators in Taylor series of angular momentum L, which should span the complete Hilbert space for the crystal field, then the A00 term scales with L to the power 0 and the A04 term with L to the power 4, such that this then becomes the Stevens operator A04 and the Stevens operator A44 and A minus 44. Such that if you want to make effective operators in terms of angular momenta, you can immediately do that from here. These kind of effective operators have been worked out completely for atomic shells, and for atomic shells in potentials, they are most probably the most efficient way to do these kind of calculations. However, if you want to include charge fluctuations, which we want to do later on, then having to work with these kind of effective operators becomes much more involved. And in order to write down the Hamiltonian in terms of second quantization, we can also look at the operators just based on the scattering energy between a state with m and m prime. So have a look at epsilon m and m prime that comes from a Hamiltonian with this symmetry. And there we can look that our d shell splits into EG orbitals and T2G orbitals. We know explicit representations of those if we assume that our C4 direction of the cubic point group is in the x, y, and z direction. Then the EGs are the x square minus y square and the z square, whereas the T2Gs, x is missing, y, z, y is missing, and z is missing. We can relate them to the spherical harmonics. This is d2 plus d minus 2, where this is Lm notation. This is square root of just the d0, and this is square root of a half I d1, d minus 1, plus d1, this is square root of a half d minus 1 minus d1, and this is I square root of a half d minus 1 minus d2. Now with that we can also guess or understand what our epsilon m m primes are in our Hamiltonian. Sum over m m prime, epsilon m m prime, a dagger m sigma a m prime sigma. And we have the 2 is equal to epsilon minus 2 is equal to the sum of the EG and T2G energies. The 2 and the minus 2 are a linear combination of x squared minus y squared and xy, such that the sum of the two energies is the energy of an EG and a T2G. Now epsilon 1, 1 is epsilon minus 1 minus 1, and both of them are t to g, so that is e t to g. Epsilon 0, 0 is equal to EEG, because that is a dz square orbital. And then we have the off-diagonal elements between 2 and minus 2. Epsilon 2 minus 2 is epsilon minus 2, 2, which is equal to EEG minus E t to g divided by 2. On a single orbital level, this defines a 5 by 5 matrix, and if you diagonalize that, you should get exactly the real harmonics out of the spherical harmonics as their eigenstate. Now let's get back to the microscopic origin. Of these interactions. And let's have a look at a model to get some feeling where these energies come from. And if you now do modern DFT calculations and just calculate the potentials, then for example in nickel oxide you will find that the non-spherical charge distributions will get you an energy splitting between the T to Gs and the EGs of the order of 10 milli-electron volt. The experimentally observed energy splitting is of the order of 1 or 1.1 electron volt. So it's really only 1% or so that comes from the non-spherical charge distribution in your system. In a 3D transition metal oxide. Now, in our model, I can make two sides, side A and side B. And let's just have a look at p orbitals. And I'm going to take p orbitals not because I want to make models of p orbitals, but for p orbitals I only have to consider 3, whereas for d orbitals I should consider 5. So this is just notation convenience. I have my pz orbital that can hop to a pz orbital with hopping pp sigma. They point towards each other such that the overlap is large and the hopping is large. Then I have my pi orbitals, making a pi bond, which is the px, or in this case the py orbital. I have, in terms of energies, my orbital A and my orbital B. Then I have the interaction of the pz orbital, making the antibonding state, and the bonding orbital. And I can do the same for this is the pz antibonding, and this is the pz bonding orbital. I can do the same for the px and py orbital. And as our hopping is smaller, the energy splitting that we get is smaller. And those are the px and py orbitals. Now if I assume that the atom A and atom B are the same, then the energy it costs to move an electron from B to A is a charge fluctuation, so epsilon B is epsilon A minus U. So that's the energy difference that we have here. And of course, if they are different atoms, that energy difference might be different. Now the energy that we have here for the change of the pz orbital is plus minus, in perturbation theory, pp sigma square divided by u. And I assume here that pp sigma is much smaller than u. And that of course is a logical assumption, because we want to work with crystal fields where we assume that our charge fluctuations are small. And we can do something the same for the px or py orbital, and that is plus minus pp pi square over u. And again we assume that pp pi is much smaller than u. Well, in my plot here I furthermore assumed that pp pi is small compared to pp sigma. And our crystal field that we now have is where we just focus not on both atoms, where we have a bath and an atom, but we only looked at a single atom, and we see that we get an effective splitting between the pz and the px orbital, and that energy splitting is pp sigma squared divided by u minus pp pi squared divided by u. So in order to calculate your crystal field's energies, you have to look at a detailed balance between both the Coulomb energy, the on-site potentials, as well as the kinetic energy gain that you have in such a model. And it is this detailed balance that making these kind of calculations so hard. You really have to be accurate and include all these interactions. You can calculate crystal fields on a mean field level, but you do have to have complete, well-defined basis sets, have good convergence, because you're looking at large interactions on scales of several electron volts, maybe even Rydbergs, that partially cancel each other, and it is the difference between these large energy scales that then give rise to the smaller energy differences that you get. You have in both cases a large bonding energy or an anti-bonding energy, and it is the difference between the anti-bonding energies that what we call our crystal fields. That also explains why it has been so hard through history to accurately calculate these kind of crystal fields. And I would say that only since the 1990s or 2000s our density functional theory codes have become accurate enough to really give predictable values of crystal fields. I will show you in a later video the example of nickel oxide, but this slightly gives you an idea of what goes in there. And there you will see all the details that you have to enter to calculate such kind of energies accurately. That doesn't mean that all calculations before 1990 are wrong. People very often find certain approximations and methods that work for certain classes of materials. Very often, because you had cancellations of errors, I can make a lot of error in the calculation of one energy level, and as long as I make exactly the same energies for the other energy level, your energy difference will still be fine. And this cancellation of error is a very powerful tool that we have. I would say tool that we have in many particle physics. We never need to know total energies. We're only interested in energy differences. That's very good because it's extremely difficult to calculate the total energy of the inner bound electrons in an atom. But in all our experiments, they don't really react, such that we can just neglect them, and we don't have to do all these energy levels with very high accuracy. We just assume they're filled, and that's it. And we assume that they're the same before and after we do our experiment, and during our experiment, such that we can neglect them for the energy differences that we observe. And that is true partly of the methods developed to calculate crystal fields in earlier days, but then you should be aware that you cannot just extend one method developed for one class of materials to other classes of materials. So if you have a method that works for oxide, it must not also work for sulfides or fluorides. Nowadays, with good density functional theory calculations, you can do that, but it's non-trivial. So much on the microscopic origin of the term splitting that you get in atoms for single configurations when you put them in a non-spherical environment. Now let's have a look what this has on the many electron ground states. Here we namely only looked how our orbital energies are changed. But we're no longer in a mean field theory where you can just take orbitals and fill them. We have locally our many body multiplets, and we have to now look how these effective potentials influence the many electron states. And for this we can look symmetry. Based on symmetry we can already understand what kind of eigenstates we should expect. And let's have a look at an example. And as an example I'm going to take H electrons in the D shell, which you find, for example, in nickel oxide. Now our D shell splits into EG orbitals and T2G orbitals, and for nickel and nickel oxide this energy difference is about 1.1 electron volt. So compared to the several electron volts of the difference in the multiplet energies, it's a sizable energy. Now, first of all, we can have a look at the atomic terms that you find for a D8 configuration, and that is the singlet S, the triplet P, the singlet D, the singlet G, and the triplet F. So on left top, 2s plus 1, and in capital letters, the total angular momenta. And now we can look how they branch into the irreducible representations that we have because of the cubic symmetry. Well, we already discussed before that an angular momentum 2 states, so a D state, branches to EG and T2G. And it's a singlet EG and a singlet T2G because I'm not considering spin, so this is without spin-orbit coupling. Now an S state is single-fold degenerate, completely spherical symmetric, so that has to branch into the A1G. A p orbital in cubic symmetry stays degenerate. There is no difference between the x, y and z direction. It's a triplet and it becomes a triplet T1G. The G state is something that we have to look up, and if you look at tables you will be able to find how G orbitals branch. And the F orbital branches into an A2G, a triplet T1G, and a triplet T2G. Now the A is single-fold degenerate, which fits with the S, the T is three-fold degenerate, which fits with the P, the E is two-fold degenerate plus the T three-fold degeneracy of the T gives you the five-fold degeneracy of the D, and here we have 3 plus 3 for the T is six-fold, plus 1 is a seven-fold multiplicity of the F state. 1, 3 and 3-fold degenerate, and the F has 7 2L plus 1 states. Now let's have a look at the triplet sector. So I'm going to look at the D8 eigenstates for S is equal to 1. So we focus on the triplets. That makes sense because the ground state has a triplet character. And in the atomic limit we have the triplet P and the triplet F, which is the spherical limit. Then when we introduce a weak field, we know that the P stays the same and becomes a triplet T1, G, and the F splits into a triplet T1G, a triplet T2G, and a triplet A2. Now we can have a look at the strong field limit. And in this case, we have here a splitting just continuing, becoming a triplet T1G. We have the triplet T1G here, that becomes together with the triplet T2G, a near degenerate state. And then we have the triplet A2. Instead of looking at the many electron states when Coulomb interaction is much weaker than the crystal field, we come back to a single electron picture where we say here we have an T to G6, Eg2 configuration. The T to Gs sit at lower energies, so we fill them first, and then we have 2 electrons in the Egs. That allows you to make a spin 1 state. And then here we have the T to G5, Eg3 configuration. There are 3 ways you can make a hole in the T to G orbitals with spin up. There are 2 ways you can make a hole in the Egs with spin up, such that we have 3 times 2 is 6, 2 T representations there. And then we have the T to G4, Eg4 configuration. So with that you go from the atomic states to split states to these states where you have basically single Slater determinant representations on a non-interacting level. If you would connect them, then we have the A, and this should be a straight line, the T2, which is a straight line, then the T1 and the T1 continuing there. And this really should be just a straight line. The 2 states of T1 symmetry mix with each other, whereas the states of T2 and A2 symmetry are just linear dependent in their energy on the size of the crystal field. So on the horizontal axis we have EEG minus E T to G. We can now have a look at explicit representations of these states. And I will just have a look at the ground state with S set is 1. And this is the state where we remove an electron in the x square minus y square orbital, and we remove an electron in the z square orbital out of the vacuum. And our vacuum in this case is a filled d shell. So we're in a language of holes. Now our triplet T1 with S set is 2 is given by a linear combination of a state where I have an YZ with spin down and an XZ with spin down plus an annihilation of the XY with spin down and the X square minus y square with spin down generated out of the vacuum. And depending on the size of the crystal field, alpha and beta take different values. For the case where the crystal field is infinitely strong, alpha and beta are plus minus 1, are 0 or 1. For the case where you're in the atomic limit, it's square root 2/5 and square root of 3/5. And then somewhere in between there, this changes. Now, this is something that you will find very general in atomic physics and crystal field theory. The ground state is represented by a single Slater determinant. And actually that is true for all D configurations except for D3 and D7. And you have some excited states that are given by a combination of Slater determinants and just are correlated states. Such that if you want to describe the ground state, you can use mean field theory because you are able to represent it by a single Slater determinant with some accuracy. However, when you think of the excited states, so the dynamics of a system, you really have to go beyond mean field theory or time-dependent potentials to be able to describe that system well. Now, crystal field theory has been used for many years. Of course, it's one of the earliest developed theories to describe solids. And it has been successful in some parts of describing materials. If you look at color centers in glasses, then there it becomes really powerful. because, well, instead of just having your atomic terms, you see that you now get many more excitations, and then when this excitation sits in the red and that excitation sits in the blue, then the green light will be passing through and you get a nice green glass. And because these excitations can be very sharp, long-lived, you are able to get nice and vibrant colors, not something where you absorb a little bit for every color, but you just absorb only a few different colors. It's not only color centers. If you look at enzymes, for example, iron in heme, then we have locally a D6 configuration. And if you think of a D6, you have roughly cubic symmetry. It's not completely cubic, but it doesn't matter if this is one degenerate level or 3 split levels. We have our T to G and EG orbitals. And if you are in the weak field limit, then we have 5 electrons with spin up and 1 electron with spin down. And this would be the heme without an oxygen bound. Now, when we bind an oxygen, that crystal field splitting becomes much bigger, such that we go to a state where all 6 electrons sit into the T to G and the EG is empty. So you make a transition from an S is 2 to an S is equal to 0 state. So iron in heme has a magnetic moment when it has no oxygen bound to it, and it loses its magnetic moment when an oxygen binds to it. Now, the way I write down my states are both single slater determinants. However, one should realize that we have here, of course, a strong competition between Coulomb interaction and crystal fields, whereas for the high spin ground state you can optimize both at the same time. For the SS0 ground state that is not true at all, such that this is just the dominant part of your Slater determinants of your wave function, the dominant Slater determinant of your wave function, and the full wave function is a combination of many. It's a highly correlated state, it's a highly entangled state, it's a state where you have strong local charge fluctuations between the T to G and the EG orbitals, which means that if you want to calculate accurate energy representations of the different states, then it becomes very important to include all those many body effects in that calculation. So if you want to know what the potential is or what the binding energy is for oxygen in your lungs and for reabsorbing the oxygen or for taking out the oxygen from heme in your muscles, then you really have to include all that many body physics. Now, these local multiplets also have huge importance for the local magnetic moments that we find in these materials. They determine the magnetic anisotropy that we have. So people are looking in magnets for hard magnets where it's not easy to just rotate the magnetic moment in your crystal, but you really have strong anisotropies. And for that you have a local crystal, or a crystal with local moments. And then the anisotropies are really determined by the interaction of the crystal field and the atomic multiplets that you have in your system. Last but not least, when you go beyond the fully local system and you include some hopping of electrons, then the fractional parentage is highly determined by the crystal field ground states that you have locally. So as such, crystal field theory already gives you quite some information on your system. Well, it's not perfect. Solids are not just single atoms sitting next to each other, but you really have this kinetic energy where you can exchange charge between atoms. And you notice this most and for all that when you try to calculate parameters or fit parameters, your crystal field parameters, to an experiment, and you do this either for the magnetic anisotropy, so at really low energies, or you do this for an optics experiment where you make transitions between the local levels, or you do this for conductivity where you take out an electron locally and you place it on a site somewhere far away, photoemission, inverse photoemission. you will find that for each of these cases you will need slightly different crystal field parameters. Another way of stating this is to say that your crystal field parameters are energy dependent. If you want to put this very small Hilbert space into a Green's function, then you will notice that you get a self-energy with a strong dispersion, and depending on the configuration and the states that you have, this really influences the local energies, such that, if you really want to compare these kind of excitations and experiments, you notice that the Hilbert space on which you try to describe your system is too small to really get just static parameters that you can use between different experiments. Well, the combination of this with the fact that it's not historically clear where the crystal field parameters come from, of course, made this an extremely hard problem to solve, which also explains why it took almost 70 years between the basic idea of the theory and having a quantitative theory with really predictive power through the different fields and materials. So in our next video we will continue and see how we can extend crystal field theory to ligand field theory, where we then explicitly include charge fluctuations between the local atom and the bath, or its chemists would call it the ligands within your crystal. For now, thank you very much, stay healthy, we see each other later.